A compounding event is an event that includes two or more simple events. That's all it means. When it's compound, it's more than one, it's two or more things taking place. Such as flipping a coin and rolling a number cube. Okay? So, let's talk about what happens. If you're looking there at the first page, what are the possible outcomes of flipping a single coin one time? What are the possible outcomes? Heads or tails? Everybody understand that? If I flip a coin, those are my chances, right? What are the possible outcomes for rolling a standard number cube once? 1, 2, 3, 4, 5, and 6. When you have compound events, you can figure out the probability by creating tables or lists. It says complete the list for all the possible outcomes of flipping a coin and rolling a number cube. Notice, they said heads 1, heads 2. What am I going to put next? Heads 3, heads 4, heads 5, heads 6. Then they went T1. So tails 1, tails 2, tails 3, tails 4, tails 5, tails 6. I want you to notice something. How many possible outcomes are there now in my list? There's 12 outcomes. How many outcomes were possible with this? 2. How many outcomes were possible here? What did I do with these two numbers to get my list? I multiplied them together. What happens when you're figuring out how many times something could happen? If there's 2 events possible in the first one and 6 events possible in the second one, when I create a list or a table, there should be a total of 2 times 6 things that are possible. 12 possible events. Does that make sense to everybody? So, there's 12 possible outcomes for this compound event. Now, they actually asked me to flip a coin and roll a number cube 50 times. Okay? We're just not going to do that. We're just not going to take the time for every student to do that. Just not going to do it. What do you think the outcome would be experimentally? What should it show? If I did it 50 times. If I did it 50 times, I should end up with 25 heads total, 25 tails. Is there any way that these are going to be equally spread out? If there's 25 of them total in the heads and 25 total in the tails? No. Okay? They can't possibly come out because 25 isn't divisible by 6. 6 things going across.
Wait, I have a question. Why is this
Because this would be a heads 1, a heads 2, a heads 3, a heads 4. That when I flipped my coin that I got a head, when I rolled my die I got a 1. It's a way to record the data if we actually took the time to do it in class. Okay? So, out of curiosity, would you expect your probabilities, would you expect these to all be the same? Do you think there's just as much chance of getting a heads and a 1 as there is a tails and a 6? No. I mean, if you're rolling it, there should be, theoretically, right? Should be the same. But if I only roll it 50 times, is there any way that they're going to be the same? No, because 50 isn't divisible by 6. Okay? Turn the page. Compound events. More than one thing taking place. Here, there's 3 different types of drinks. There's 2 different sizes of drinks. There's small and large. There's soda, water, and cocoa. How many possible outcomes are there? How many possible outcomes? 6 possible outcomes. From a theoretical standpoint of view, it should be that I'd have as many people with a small soda as I do with a large cocoa, if I was looking at it that way. One of the reasons that we do things experimentally is because if I were in a store, I might want the data when I'm purchasing my supplies to find out, do I need to order as much soda as I do cocoa? Well, look at the table. What's the least likely thing to happen according to this table? Out of everything that's there, what's the least likely to happen? A large water. That's the least likely. What's the most likely? A small water. It's got more numbers. In order to figure a probability of an event, I've got to know one thing first. What do I have to know? Nothing's different than yesterday. What do I have to know first? I got to know the total. Because when I figure the probability, it's the number that the event happened divided by the total outcomes. So, let's add this up. 77 and 68. 145. 98 and 45. 143. 143. 60 and 52. 112. 145. 143 is 288. 288 and 112 is 400. There are 400 individual events that have been recorded. Everybody see that? What is the experimental probability that the next drink would be a small cocoa? Well, how many times did small cocoa appear in the table? 60. So the experimental probability of getting the next one being a small cocoa would be 60 over 400. And I should simplify that. It's easy to drop the zeros. 6 over 40. Still divisible by 2. 3 over 20. Let's go ahead and talk about what that is as a percent. 3 divided by 20? 0.15 or 15%. Before I calculate an experimental probability, what do I have to know? I have to know the total of numbers that was attempted. How many trials were made? Then I can look at how many of those trials came out with the results that we're talking about. Everybody okay so far? A jeweler sells necklaces made in 3 sizes and 2 different metals. Okay? Yep, should be the next page in. No, one more after that. A jeweler sells necklaces made in 3 sizes, 2 different metals. Use the data from the simulation to find the experimental probability that the next necklace sold is 20-inch gold necklace. What do I have to know first? Okay. So again, I'm going to add up going this way. 12 and 16 is 28, and 5 is 33. 22 and 8 is 30, and 12 more is 42. And my total would then be 75. Everybody good with the total? Whatever my experimental probability is, my denominator starts out as being a 75, the total. They said 20-inch gold. Here's 20-inch. Here's gold. What number do I put there? 12. It can't. They're definitely both divisible by 3. How many times does 3 go into 12? 4. How many times does 3 go into 75? 25. 4 over 25. It doesn't say, so I would take it this way, or I would take, this would be, yeah, this would be 16% or 0.16 or 16%. And I would take any one of those explanations. Okay? With a compound event, experimentally, what do we have to find first? The total. You take the number of times it happened divided by the total number of attempts. Good? I want you to flip to the guided practice and look at number 2. Okay. At a car wash, customers can choose the type of wash and whether to use interior vacuum. Customers are equally likely to choose each type of wash and whether to vacuum or not. Use a simulation to find the experimental probability that the next customer purchased a deluxe wash and no interior vacuum. Describe your simulation. Okay? How many possible events are here? 3. How many possible events are here? 2. Okay? First off, let's talk about things that simulate 2 really well. What can I use to simulate something that has 2 outcomes? Flipping a coin. Flip a coin. Heads, yes. Tails, no. could I do to simulate something that has 3 outcomes? I could create a spinner that has what? 3 equal parts. Can anybody think of another thing that we might be able to use? Because we can't always just make a spinner that has 3 equal pieces to it. What's something that I could use that I could find a way to divide into 3 equal parts that most people have? You could use a die, right? A die has 6 sides, but I could use a die, and I could let 1 and 2 represent standard. I could let 3 and 4 represent deluxe, and I could represent 5 and 6 be superior. Now, if I did that, if I rolled a die and I flipped a coin and I recorded the data, I could do that once or I could do it 1,000,000 times. I could use that data then to make a prediction about what the next customer would do. The more times I do it, the better the data is. The only thing that's important is whatever you select has 3 equal chances to be selected for the type of wash and 2 equal chances for whether you're going to vacuum or not. There are infinitely many possibilities. This is just a possible situation. By the way, how many possible outcomes are here? Does anybody know? There are 6. How did you find it? 3 times 2. There's 6 choices. I could get standard vacuum, standard no. Deluxe vacuum, deluxe no. Superior vacuum, superior no. 6 possible outcomes. Everybody understand what we're doing? Your assignment, page 384, number 1, then 385, 4 through 10.